How are we looking? Excellent. I've got the double thumbs up from Paul, so I'm going to crack on. So, yeah, thanks for that introduction, Paul. As he says, my name's James Batham, and I'm an engineering geologist at Atkins. So today, yeah, I'll be talking to you about careers in engineering geology and geotechnical engineering. So, as I'll go into a bit more detail in a few minutes' time, it's not exclusively a career path for geologists. You can also get into it through an engineering pathway as well. But I'll try and give you a bit more detail on that as we go through. I'll talk to you about my background, so how I've ended up where I am today from starting out at King Ed's in the same situation as you guys, what the role of an engineering geologist entails on a day-to-day basis, and then I'll talk through a typical kind of project life cycle. I think that's the best way to sort of summarize what I do on a day-to-day basis. And then, yeah, we'll take questions at the end. So yeah, feel free to post those as we go. So yeah, in terms of my background then, so as I say, I'm from Stourbridge originally, parents are still there. I've only moved down the road to Birmingham over the last 10 years or so. So I did my A-levels in geology, geography, English lit, and I got an AS, which I dropped after the first year, in biology, which was the way it was done back then. I then went to the University of Birmingham, where I studied geology for 3 years. Once I graduated from Birmingham, I went straight into a postgraduate master's degree in engineering geology. Picked up bits and pieces of work experience as I went, which was really useful, actually, really good to get a bit of work experience in between uni and starting as a graduate at Atkins in 2015, so sort of over 5 years ago now. I've completed the graduate training scheme a couple of years back, still working for Atkins, and the next sort of professional step for me will be to attain chartered geologist status, which is like a professional accreditation. You may have heard of people being chartered accountants and stuff like that. Well, you can do exactly the same as a geologist. So that's kind of like where I'm at, the point of my career that I'm at right now. And here's a good picture of me on the right doing some abseil rope access inspections of a rock face. So this is one of the cooler things I get to do in my job. And that was sort of like a 20-meter high slope there with trains doing about 60 miles an hour at the bottom. So that was quite exciting. Now, so when I typically introduce myself and people say, "What do you do?" I'm a geologist. I think the first thing that comes to people's minds is oil and gas mining. Well, no, I don't actually have anything to do with that in my day-to-day job. Or perhaps people think, he likes looking at rocks and climbing volcanoes and doing whatever this guy is doing with lava, for example. I don't do that either. So yeah, it's not what geology is all necessarily about. And yeah, the other one that people always go to is, Jurassic Park, you must be a paleontologist, or Ross from Friends, or archaeologist, etc. I'm a fan of Jurassic Park, hence putting this picture in, but that's about as far as it goes from that perspective. So yeah, my day-to-day career as a geologist doesn't involve any of those sort of typical things that you might expect a geologist works in. And I'll say at this point in this talk that I'm going to talk about engineering geology as one pathway you can go into from doing a degree in geology or engineering. But the fact is, there are loads and loads and loads of options out there, basically. I'm only going to talk about one small sector of it. So yeah, if geology or engineering is something that interests you, there's a couple of links here that give you an idea of like the wider options that you have from doing geology. And I like this quote here that's from the Geological Society, saying about how geologists are crucial in meeting society's future challenges and meeting the UN Sustainable Development Goals, helping countries meet the Paris Agreement for climate change. So geology is really not all about fossil fuels and mining and that kind of thing. It's actually a really important science area to get into when looking to the future. So to dive into the engineering side of things then, this slide hopefully helps to sort of break down a few of the different aspects that I might talk about in the next half an hour or so. So I'm an engineering geologist, which is someone who is trained as a geologist at university and then goes into working in civil engineering or environmental management. Civil engineering is anything to do with built environment, so buildings, railways, highways, energy supplies, etc. Geotechnical engineering is kind of a cross between those two. Don't worry too much about this terminology. I'm just trying to break it down a little bit. But also, we can work in environmental management and things like contaminated land, looking at mitigating environmental impacts as part of our role. And I've just put these 3 points at the bottom here. This is quite, this is not a hard and fast set of rules in terms of A-levels and degree courses. This is just a guideline. That's why I've put the asterisk after the A-levels there. Typically, people who I work with in engineering, geology and civil engineering will have A-levels in geology, geography, chemistry, physics, maths, or some combination of them. It tends to draw people who've done those A-levels. But as I say, it's really not hard and fast. Digital skills are really important. So anything to do with IT or creative design, languages, obviously, if you want to work abroad. And yeah, again, some typical degree courses would be to study geology or civil engineering or environmental sciences at university. So jumping into engineering geology, the basic reason that we have engineering geology as a science is that anything that is built is affected by the ground, and everything that is built requires an understanding of the ground conditions that are underneath it. So for those of you who do geology A-level, you'll know that the ground is really variable in terms of different rock types. Different rock types have really different properties. They're formed in different environments, so they have variety to them. In addition to that, you've got structural elements like faulting and folding that can make the ground vary greatly over a small area. And as geologists, we work with materials that are really different to steel and concrete. So steel and concrete are like designed and manufactured, whereas the rocks and soils beneath the ground are really not. They don't really adhere to the rules, if you like. And so there's a few prime examples on the left here that I'm going to go into a bit more detail on in a moment. And yeah, we'll be concerned with ground conditions, like if the ground is really soft or hard, or if it's unstable and prone to movement, if there's water in the ground, if there's any pollution in the ground, or if there's any holes in the ground that things can fall into effectively. So the classic example of an engineering geology issue is the Leaning Tower of Pisa. So basically what happened here was architecturally, struggle to say that, they built a really nice looking tower. You know, from a structural perspective, it's great, looks beautiful. But what they didn't take into account when they built it was that the soil they were building it on was effectively like really soft Play-Doh, really soft clay that had formed in a river valley. And when you put a heavy weight onto that, effectively the object you've put onto it sinks into it. So basically, yeah, they didn't take into the fact they were building it on really rubbish ground. They put a massive weight on it and it basically sank on one side. So engineering geologists assess the ground before things get built to make sure that things like that don't happen. You may well recognise this, or I hope that a lot of you do anyway, if you're from the Black Country area. This is the Crooked House down near Himley, up towards Dudley. So this is another example of infrastructure being affected by the ground conditions beneath it. So what's happened here is over hundreds of years of coal mining has taken place beneath Dudley. This used to be a perfectly fine building when it was first built, but what's actually happened here is the coal has been mined away from underneath it, deep below the ground, and over time those disused coal mines have collapsed, and that's led to subsidence. So there's a lot of really old buildings around the Black Country that are subject to subsidence like this. So again, that's another way that the ground can affect buildings or infrastructure generally. And yeah, we aim to sort of make sure that things like this don't happen. So this is a pretty major landslide that happened up in North Yorkshire back in the early 90s near Scarborough. And towards the top left of the picture, you can actually see there was a quite fancy hotel there that basically went down with this landslide when coastal erosion caused this landslide to occur, basically in the soft soil up there. No one was hurt, fortunately, so that's good. It was evacuated in time. But yeah, as climate change happens, as a result of the warming climate, increased rainfall, coastal erosion as sea level rises, geologists are important in basically, making sure that events like this can be avoided, or they can be mitigated against or predicted. So that's another way that we apply our work. And the bottom line is that basically, everything that gets built has to be in contact with the ground, or be within the ground, in fact, in some way or another. Unless it's floating in midair, it is affected by the ground that it's being built on. So yeah, the workload that we have is kind of like limitless in terms of, as much as people are building things, they're going to have to consider the ground, and that's going to affect the design of buildings, railways, foundations for anything really. And what we try and do is basically to communicate ground risks through producing ground models. So this is a typical model that we might produce where we've got the geological setting on it. We've labelled up some of the hazards, so potential blocks of rock falling from a cliff down onto a road in this case, and we've sort of taken in the potential the potential areas that are going to be affected in terms of the residents at the top, the road at the bottom of the slope, and basically we communicate that to our clients to say, these are the areas that are affected by these issues. You need to consider it when you build whatever it is you want to build. So there's also a pretty serious side to our work, really. So it's all about managing risk, and unfortunately, a few events in the past have kind of like brought engineering geology to the forefront and actually made people realise how important it is, through tragic consequences in some cases. So some of you may have heard of the Batham disaster that happened in South Wales in 1966, and this was where, at the top of the picture here, that was basically a huge pile of coal mine waste had been piled up from a colliery above the village of Batham, which is at the bottom of the slope there. And due to that slope, which was basically a pile of just rubble from a coal mine, not being properly designed or maintained, during a period of heavy rainfall, it actually failed and created a landslide that went down onto the village, took out the primary school, and actually killed 116 children and 28 adults. This was kind of like a bit of a wake-up call for the government of this country, and for sort of bringing in health and safety regulations across the country, and making sure that engineering geology was applied to make sure that ground conditions were taken seriously and to prevent disasters like this happening again. And it's a really relevant area to get into. Basically, if you're considering a career in something like this, then you're definitely not going to be short of work, to be honest. It's looking really healthy as an industry right now. So obviously, post COVID, there's going to be a big push to sort of invest lots of money in infrastructure, but that was kind of happening before COVID came around anyway. So here are just a few examples of that, of kind of contemporary civil engineering projects that are going to be going on for the next few decades, to be honest. Climate change is going to be a big driver in people wanting to spend more money on things like coastal defences, for example, and invest in green energy. So we do a lot of work with like building wind farms, for example. New housing, there's always been a push for new housing over the last few years, building on sort of more and more marginal sites where perhaps people wouldn't have built houses before because the ground was a bit hazardous, but now people do want to build on there because of land shortages, basically. And we've also got major projects like High Speed 2, the new high-speed railway between Birmingham and London that's being built. I've worked on that, and I think, to be honest, most of my colleagues have worked on it at some point, because it's such a ridiculously big mega project that's going to take up a lot of the industry and is going to be being built for the next 10, 20 years, to be honest. So yeah, a lot of what's going on today will still be going on by the time that you guys get to be at a graduate level. So it's a very buoyant area to enter into. So I'll go through like a typical project life cycle, basically. So I work for Atkins, who are a consultant, and basically, yeah, we're a global engineering and project management design consultancy. That's the kind of tagline. So what would happen in our day-to-day role is a client, so that could be a government organisation, perhaps like Highways England or Network Rail, or it could be a council or a housing developer or someone like that, will come to us. They will say, we need to build XYZ in this location. So, for example, yeah, they could say, this is the Scottish Highlands, this is the A9 road on the left-hand side. Transport Scotland came to us and said, we need to build another 2 lanes of road here, make it happen. And you look at that picture and think, where is another 2 lanes of road going to go? This is kind of like the sort of problem solving that we have to deal with. So when we start a project, the first thing we look at as engineering geologists is what information is actually already out there by doing a desk study. So a lot of information is actually already out there before we sort of even spend any money looking for new information. So the geologists amongst you may be aware of the BGS maps that are out there. British Geological Survey produce really detailed geological maps actually that cover the whole of the UK. So this is the Stourbridge area. Stourbridge is kind of that little red pointer sort of in the middle there. And straight away you can see there's quite a lot going on geologically. All of the little dots are actually borehole records where people have drilled boreholes and they've got a core that they've logged, and that will give you details of what geology is present. Around the Stourbridge area, it's kind of like you've got loads of sandstones to the west of the town, and then towards the east you've actually got all of the coal measures, which is what was historically mined. Lots of made ground, which is basically artificial fill material that humans have put in there as well. So we basically review all of that information to get an impression of what the geology of a site is. We then look at historic maps as well. So you can tell a lot about an area by looking at maps from 100 or so years ago. This is critical in working out if you've got a history of mining at a site, for example. So this is a map from, I think, the very early 1900s of Amblecote. So obviously near King Heads. Specifically, it's sort of Withymoor over towards that way, if you know that area. And yeah, at first glance, it's like, right, okay, it's a historic map. Not that much going on. There's a few less houses, perhaps. If you actually start to dig down into the detail, everything that I've squared in red there is something related to mining. So you can tell that, yeah, 100 years ago, it would have looked a lot different. And the fact that there's mines there means potentially there could be big holes in the ground, basically. They could have been backfilled quite badly. There could be potentially pollution in the ground. And if you were to look at a map from the modern day, no sign of that at all. So that's one thing that we do. We sort of review the maps and the historic maps to see what a site's history is. And if anyone lives in Withymoor, don't panic. I'm sure that they did a very good job of backfilling all the mines. So other things we need to consider are things like potential for buried, unexploded bombs, which was something that sort of blew my mind when I first heard about it. But if you want to build something, if you're doing it in an urban area, for example, around Birmingham or the West Midlands, there's actually quite a lot of basically bombs that were dropped during the war that sort of didn't explode, went undetected and remain buried to this day. So we have to sort of do an assessment of sites to see if there's a risk of this being something that's buried in the ground before we build anything. I've included that little screenshot in the top left there because over the weekend they actually found a bomb in Exeter, down in Devon, and they had to bring the army in to sort of detonate that, and there's a pretty spectacular video of it on the BBC News website. But I'd be willing to bet that was probably found on a construction site where they were building something. So that's another aspect we need to look at. And also we just go out to the site is always a good way to start a project and actually walk the ground, see if you can find anything for yourself that isn't on the maps. Talk to the local farmer. He's normally the best person to speak to. He'll know if there's an area of the site that's always flooded, or if there's an old mine shaft that's maybe not recorded or anything like that. So that's where we start a project. Then we move into something called ground investigation. So a lot of my time is actually spent managing work like this. So we literally dig holes in the ground effectively to find out what the soil types are or rock type is beneath a site, to work out how the ground conditions are going to react when we build whatever it is we need to build. So this can be, as I say, pretty low tech really, guys with shovels digging holes to take samples or using JCBs. But we also drill lots of boreholes. So these are using slightly bigger bits of kit like these here. These can get down to sort of hundreds of meters depth if we need to. So these are photos that I took on the High Speed 2 ground investigation. And basically what a borehole does, if you're not aware of it, is it basically extracts material from the ground like this as a core. So we can then review that on site. We make what we call a log of it, record all the different soil or rock types that are present, and create a detailed log of that, and take lots of samples of that as well. So we take representative samples of the ground. This can be to test either for the strength of it, or we also test to see if it's got any contamination in it. So if any, if you're working on a site that was an old factory, for example, we need to test the ground to make sure it's not got any nasty chemicals that are left there from when it was a operational factory. And we undertake testing on it. So as I say, testing will pick up any contaminants. It will see how strong the ground is. That will let us know what sort of foundations we need to use when we come to design some infrastructure. Or it will identify any particularly weak areas of ground that might need to be remediated, for example. And we also, after we've drilled boreholes, sort of sometimes leave pipes in the ground just to basically monitor the water levels in the ground over time, because the water content of ground is really important. It actually, as well as potentially flooding any holes that we dig, it can actually weaken the ground from an engineering perspective, and we can monitor for any gas in the ground as well, or if the ground's moving. And all of this, if any of you are into sort of data at all, basically all of this creates a massive data set from all of our site work. Previously, this would have been a huge paper report that was like 1,000 pages thick, but obviously now it all gets sent to us as digital information. And this is where we start to actually get more from a sort of geological side of things into a engineering side of things, I guess, because this is where we start to create digital models. So here, each of these sticks is actually a borehole, and the colours represent different ground conditions that are present, and we can start to overlay the actual engineering onto this. So this is a proposed new station down in the south of England, and this is a good way of sort of showing our clients, this is the information that we found. This is how what you want to build fits in with that ground information that we've got. So what do? We don't just sort of play with the soil and the rocks effectively and deal with that side of things. We actually take it a step further than that. As I say, moving into more of an engineering rather than a geological perspective, and we design earthworks, so soil, slopes that roads and railways run on top of. In addition to earthworks, we look at foundations, we look at retaining walls. So foundations being effectively the sort of concrete base, if you like, that a building sits on to stop it sinking into the ground. And yeah, all of this is done digitally using different software packages, basically. Not so much, handwritten sheets and sheets and sheets of maths calculations these days. A lot of it is just done through software. But for any of you who are more interested in the engineering side, this is basically what we do a ground investigation to obtain ground information, but then that feeds into an engineering design. And here's an example of that. Basically, on the left is a slope model that I put together based on some boreholes. You plug that into a piece of software, and that tells you basically what angles are safe to build your slopes at. And then that fed into a new build railway earthwork on the right hand side. So yeah, drill a borehole, obtain parameters of strength for different types of ground, run it through some software, and that gives you an idea of what you need to build. And engineering geologists will be present at the construction stage of projects as well. This is a new road that's being built down in South Wales. We'll go to site to basically make sure that they're building it correctly, they're building it to the design that we've asked them to. Yeah, we design all sorts of things basically. Depending on each project, it's pretty bespoke. But yeah, as long as we sort of meet the initial client needs, then that's what we set out to do. So here, for example, this road is, you can see on the left at the top there's kind of like the existing road is on a really high level retaining wall, and they wanted to fit another 2 lanes of road in. So we're having to build up this new level by putting retaining walls into a really tight area with some quite bespoke design. And yeah, that's what we'll do at the construction stage. And then we don't sort of just leave it there either. So we'll be present through from the initial desk study to the construction, but then once something's been built, we pop out to site as well to basically check on it over time, make sure that it's not degrading with time. And to be honest, a lot of our work, so for example, this photo that I took here is looking at older infrastructure such as the railways and motorways of this country that are built. Well, the railways are sort of 150 years old now, so a lot of the earthwork and rock slopes on the railways are in not the best condition. So a lot of our work is going out, looking at these existing earthworks and cuttings and saying, right, okay, we need to put some rock netting on there or similar things to that. So it's kind of asset management is what they call it, but it's long-term maintenance of structures and stuff. So I think I'm slightly under half an hour there, but I've very much whizzed through that. Sorry if I've spoken quite quickly, but I'm happy to take as many questions as you have. I realise that might have been a bit of a brain dump. But yeah, that's a brief summary of what I do and what engineering geology is. Hopefully it made sense. And yeah, please fire away with questions.
That was great. Thank you so much, James. That was, yeah, really good and interesting to be linked to the local kind of things that are going on. And yeah, basically, students, any questions, type them into the chat and they'll come up, and I'm sure James will do his best to answer them.
I can yeah, everyone's probably just in stunned silence. Like, what has that guy been talking about? I know that you sent me those questions that people had sent in advance, so I can kind of talk over those for a minute if you like. So I know there was a question about what degree basically is best to take. As I say, I'm a geologist, so that's what I did at uni. I'd studied geology, but a lot of my colleagues went down the civil engineering route, so you can kind of get to do similar day-to-day stuff as me from doing civil engineering as well. And I work with people who do the contaminated land side of things, if that's what you're more interested in. You could probably do environmental science at uni to get into that area. But you don't necessarily have to do a degree as well to get into this sector. You can get into it by the apprenticeship route, so that's always worth considering as well. And someone asked about basic skills as well. I think really it's quite hard to answer that one, but I think increasingly things to be, if you're interested in the more engineering side of things and design, there's a lot of focus at the moment of people who are good at like coding and who can use CAD, so like digital drawing tools and stuff like that, which I know you can do like courses on that are kind of free online. So those are good things to be aware of.
Okay, we've had a couple of questions come through. I don't know if you can see them. Has any of your work been overseas, and do you travel a lot in your job?
So I haven't been on site overseas is the short answer, but I have worked on projects that are overseas. I was working on one job that was a project in Central America, basically, for quite a long time. That was really interesting, sort of seeing how people from different countries deal with, doing the ground investigations and stuff like that. And yeah, we do get a lot of projects that are overseas, to be honest. It kind of just so happens that I haven't really worked on that many of them, I guess. But if you work for a company such as Atkins, and you really want to work overseas, then it's quite easy to get into that, to be honest, especially if you pursue it. And in our industry, there are a lot of jobs in places like Scandinavia and Australia, North America as well. So yeah, if you're desperate to get out of Stourbridge, then yeah, you can definitely get into working overseas in this area. And then I suppose the travel one is kind of linked. I mean, I've traveled all over the UK a lot. I've worked from like literally Inverness to Cornwall, and been on site in those places. And yeah, I go out to site. Well, I suppose this year, I think, apart from the last couple of weeks, I was going out to site like at least once a day. And then in a couple of weeks' time, I'll probably be on site for a month or two. So you do get out and about a lot. It kind of depends which company you work for, and what kind of company you work for depends on how much you're out on site. So working for a big consultant like Atkins, you tend to split your time between being in the office and being on site. Whereas if you work for like a ground investigation contractor who are drilling the holes in the ground, you'll be out on site and traveling around constantly. So it depends what your preference is, really.
Cracking. Thank you ever so much. Okay, well, I'm not seeing any other questions cropping up, so I'd just like to finish by thanking you a great deal. That was particularly interesting. Yeah, so I mean, not going to go on about it, but I did engineering as a degree, so there's elements of that I personally was like, oh yeah, very good. But that's fantastic. I'm sure the students got a great deal out of it. So thank you ever so much, and I will see about stopping the recording now. And yes, just thank you ever so much.
Awesome. Not a problem.
Thank you for coming through from the students as well.
Good.
So that's great. If any of the students email me with any further questions they've thought of, I'll be sure to pass them on.
Yeah, definitely. Please do. And yeah, more than happy for that. And cheers, everyone, for your time.
Great stuff. Thank you so much. You take care.
Thanks all. Cheers. Bye bye.